So it's basically this problem. We have ZL here. We've got a characteristic impedance Z not equal 50 ohms, right? Is that
Yes.
right? 50 ohms? And they want to find out what ZL is. So you know the reflection coefficient in general is equal to ZL minus Z naught over ZL plus Z naught. Everybody familiar with this, right? I'm just going to leave this as gamma L. So now I'm going to solve, they want to know what ZL is, right? This is one equation with one unknown, Z naught's known and gamma L's known. So I multiply both sides by ZL plus Z naught, and I get ZL plus, or minus Z naught, pardon. Y'all agree with that?
Yeah.
All right, now after that, I'm going to go ahead, since I'm trying to find ZL, I'll go ahead and I'll take this, I'll break it up, gamma L times ZL plus gamma L times Z naught is equal to ZL minus Z naught. I'm just going through the motions. Now I'm going to get everything with ZL on one side and everything else on the other. So when I look at this, I have ZL here, so it's going to be ZL over here, and it's going to be minus 1 minus gamma L. Y'all follow me on this? We're taking this that side. Now I've got this on the other side, so I have Z naught over here, and it's going to be gamma L here. It's going to be plus. So you can see that now ZL itself is going to be equal to Z naught divided by 1 plus gamma L over 1 minus gamma L. Can everybody follow me on that? And it's just by rearranging terms. Just take a good look and make sure y'all see it. Everybody good on that? So now you put in the value for gamma L. Here's where you need your calculators to do this. Remember, that's in degrees. You got to be careful about that. So this is going to be Z naught over here times 1 plus gamma L, which is 0.516 e to the j 8.28 degrees over 1 minus 0.516 e to the j 8. What?
It's 8.2 degrees, not 8.28.
8.2 degrees, okay, 8.2 degrees. This is over e to the j 8.2 degrees. Now, if you got a calculator, you can do this. Z naught is 50. So, can you tell me what that is?
I got 156.6 ohms if you want the magnitude.
What is it?
I got 156.6 ohms if you want the magnitude. But it asked.
At what angle?
Oh,
It's complicated. It's
I
complex.
forgot to write down the angle. I have the rectangular though.
That's
It's
fine.
150 plus J30.
150
Yeah.
plus J30 ohms.
Yes.
Is that right, class? I don't know if it's the answer in the book, but y'all follow me? The only thing you're doing is rearranging terms.
Okay.
And that's it. Pardon me?
No, that's easy.
And then
It's
it
just
wants
algebra.
you to make a model for ZL and like components.
Okay. So if you want this at that frequency, now just think about it. That's a resistor, right? So ZL itself will have 150 ohm resistor, if that's real, right? What about J30? Positive J is an inductor, right? J omega L would be the impedance. So you're going to have an inductor here with an inductance of J30. And that has to be J omega. Well, the frequency is 1 gigahertz, so omega is 2 pi times 10 to the 9th times L, which is something we have to find. That means L itself would be 30 over 2 pi times 10 to the 9th, and I don't know what that is. I think that's right.
Yeah.
What's the answer? I don't know.
I think it's 4.8 nanometers. I think.
Yeah, that's about right. Okay, that's that problem in a nutshell. Those are good problems because they force you to think about solving things in a reverse order. Usually, you're going to solve for the reflection coefficient. Here, you're given the reflection coefficient, you got to calculate the load. What else? There's usually 1 or 2 questions I get. Anybody else? It's a good problem. And the solutions I put up, right?
Yeah, the solutions are online. I have another question about like some of the problems said like they wanted to find like the the phaser voltage at like the end of the line versus the beginning of the line.
Sure.
What is the difference in that?
Well, voltage has magnitude and phase, right?
Yeah, is it
Why
just
don't we
like
do a problem and you'll see
Okay.
how this comes out. But first you have to find voltage. I mean, it'd be, why don't we just do it? Which problem are you thinking about?
either 222 or 223?
All right, let's do it. It's the best way to do this stuff, or find out what you're missing is just do problems. And if you don't understand how they do it, I'll work them on the board and try to make them clear. All right. Tell me which one that is.
We guess you 222.
222?
Yeah.
All right, so give me the
There's a figure you might want to look at.
just the transmission line, the voltage. Is this where?
This figure.
All right, so I got 50 ohms and a voltage source. Help me out here.
Your
I got-
voltage source is 4 cosine
Is this
omega
50
t.
ohms here?
Yeah, 50 ohms.
Okay, oh, this is a good one. And this is plus or minus 4 what?
4 cosine omega t volts.
Okay.
And then
And what about the transmission line?
the length is just it just says lambda.
It's 1 lambda long?
Yeah, it's just lambda.
That's odd. That's
And
gonna be,
then z naught is equal to 50 ohms.
this is 50?
Z naught, and then the load is
Z is 50 now?
the load is 100 ohms.
Okay. This is 100 ohms, so ZL
Yeah.
here is 100 ohms.
Yeah.
And what do they want?
Let's see.
I'm
They
gonna
want
show
to
you
find
the
first they want to find the reflection coefficient, and then the visuar, and then input impedance Zn, and then the phasor voltages at
ZN right here?
Yeah.
Okay, the Zn right here is gonna be ZL. We'll get that and I'll show it to you.
Okay.
So they want, first thing they wanted was what? Reflection coefficient?
Reflection coefficient.
Let's do it. Bing, bing, bing. So first thing is reflection coefficient. That's always the impedance you're going into, right? Minus the impedance you came from over the sum. All right, in our case, it's going to be 100 minus 50, or 50, right? Over 150, or that's 1/3. That should be the reflection coefficient.
Yeah, that is.
What's the next part?
the visuar?
All right, now, what is VISWAR? It's the ratio of peak to minimum voltage. Do you remember me talking about that last time?
Mm-hmm.
Remember I said that VISWAR, because the general equation for voltage, phasor voltage anywhere on the line, is going to be that V naught plus that you calculated. And then it's going to be times what? E to the minus j beta z plus the reflection coefficient times e to the plus j beta z. Do y'all remember me talking about this last time? Right? Now, V0 plus we can get, but here's the thing. The maximum value of this voltage, remember VISWAR, or voltage standing wave ratio, the thing, VISWAR, voltage standing wave ratio, oftentimes it's just called SWR, is going to be Vmax over Vmin. It's always positive. The minimum value it can have is 1, the maximum is infinity. Do y'all remember me talking about this? Now that'll always boil down to the maximum possible voltage will be 1 plus the magnitude of gamma L. That's when these two things exactly add. All right, you can just think about this as 1 and this is 1. Basically, it's going to be 1 plus magnitude of gamma L, and the minimum value would be 1 minus magnitude of gamma L. So if you look at this, ours is 1/3, so it's 1 plus 1/3 over 1 minus 1/3. That's 4/3 over 2/3, or it's really going to be 2, isn't it?
Yeah, it's 2.
All right, but you all follow me on that. Now what's the next part?
Part C. I wanted the input impedance Zn.
All right, now this is an interesting one. I'm going to take a second here. Remember I talked about, if you looked at Zn on a transmission line of length L, this would be the length L, and you want the input impedance at that transmission line. I put an equation up last time, and it was equal to Z naught, and then it's going to be times ZL, this is assuming it's lossless, plus J Z naught times the tangent of beta L, right? Over Z naught plus J ZL tangent of beta L. Do y'all remember me doing that last time in class?
Yep.
Take a moment and just appreciate what we're about to say. Now the key thing of figuring out what's going on is this tangent beta L. When I take a look at the tangent of beta L for this problem, it's the tangent. Remember, beta is 2 pi over lambda. You always see, you need to know that like the back of your hand. Just like V equals IR, that's the kind of level of understanding you have to understand about beta right there. Times L. Well, L is lambda, right? All right, so it's tangent of 2 pi. Well, think about that. What's the tangent of 2 pi?
Zero.
It's 0. All right? If it's 0, now follow me on here. If it's 0, what happens? Doesn't this and this go away?
Yeah, that's
And it, what? ZL times Z naught over Z naught is just ZL. And this is the beautiful thing about transmission lines. Every time you go a half wavelength, it only takes a half wavelength, then the input impedance is just the load. All right, half wavelength to there, input impedance is just the load impedance.
Is it
Half-
half wavelength as in like every pi? So like pi, 2 pi, 3 pi?
Well, what you're looking at is the tangent argument. Remember, this beta L here, think about when is tangent 0? It's 0 at 0. It's 0 at pi, when beta L equals pi. It's 0 at 2 pi. It's 0 at 3. Y'all follow me on that? So anytime beta L is pi, it's 0. Got me? And that's exactly a half wavelength. Can you follow me on this, everybody? Are we missing some people?
Yeah.
4, 6, 7. 1. Who else are we missing? I think we're missing a couple. There's 10 people in here. 2, 4, 6, 7. Well, there's 3 gone. But- That's, I think, computer support people that are, this thing ain't working. You were here today.
Is it still not working?
You tried it earlier? I mean,
It wasn't working earlier. I don't know if someone fixed it in that
well,
time.
I let them know, so I think they're trying to contact me. I can't do it right now, teaching. Anyway, okay, so that's it. What else? No.
That was CN, right? It wants the phasor voltages at the end of the line,
Yeah, good.
at the input end of the line, the load end, and the middle of the line.
That's no problem. Let's do that. All right. So here's what we need to get. Now pay attention to this part, because this is the part that people will have some trouble with. Now remember, we got the reflection coefficient, we got the standing wave ratio, just checking boxes, right? Now here comes next. Now when we talk about the complete circuit, what we need to do is get this voltage right here that I call V prime. And that is the sum of the forward and reverse going waves right here. Y'all follow me? So the way we do this, remember I said the input impedance, because it's exactly a wavelength long, is just 100 ohms. Do y'all follow me on that? So I'm going to go ahead and I'm going to say this circuit now becomes equivalent to this. I have plus to minus a voltage. I'm going to do it in a phasor domain. Frequency doesn't matter here. I mean, there's no phase offset, so it's just 4 volts at an angle of 0 degrees. Everybody okay with that? Now I put the loading, or I put the source resistance, which is 50 ohms here. And now I put the equivalent input impedance to this whole thing, which is exactly the load impedance, which is 100 ohms, right? This is 100 ohms. And now I need this value of voltage, plus to minus. Now be careful about this. Y'all with me? That's V prime. That is the sum of the forward and reverse going waves. Now please watch this. You with me, everyone? All right, so what is that going to be? Well, simple voltage division at this point. V prime right here is going to be 4 times 100 over 150, right? Or it's simply what? That's 2/3 times 4, right? Or that's 8/3 of a volt, isn't it, class?
Mm-hmm.
Everybody with me on this one?
Yeah.
It's straightforward. Now I know that, but what else is V prime? Well, it's the sum. Remember, we put the load at 0, and this is positive Z. So this distance is actually Z equals minus L. Everybody with me? And L happens to be a wavelength. With me, everyone, class? All right, so now I say that this voltage is equal to the sum V naught plus, that's the magnitude of both the forward traveling wave, and it's going to be times e to the minus j beta z plus reflection coefficient times e to the plus j beta z. That's what it is anywhere in the line. But we are at z equals minus L. Follow me, class? Can you all follow me on this? So I'm going to go ahead and do that. So this is equal to 8/3 is equal to V naught plus times, and here it will be e to the plus j beta L plus reflection coefficient at the low times e to the minus j beta L, only because z here is at minus L. Please just appreciate it. I'm trying to show you that all the subtleties you have to be aware of. Got me on this? It's not just L, it's minus L. So now when I look at that, what did I tell you about beta L? Well, that transmission line is exactly lambda long, so beta L is 2 pi over lambda times lambda, or 2 pi, isn't it? Now think about that. What is e to the 2 pi? Let me just show you what I'm talking about. When you talk about e to anything, if you have a unit vector of length 1 here, I mean a vector of length 1, this angle right here would be theta, and this would be e to the, and it would be j theta right there. Do y'all follow me? Now, if it's 2 pi, what is it? It's just 1. Do y'all follow me? If it's e to the minus 2 pi, it's 1 as well. Follow me? Can everybody see that? If you don't believe me, here's how you do it. Just use Euler. You can say that e to the j theta is going to be cosine of theta plus j sine of theta, right? Theta is what? It's the argument for that beta L, right? So if it's 2 pi, what do you get? Cosine of 2 pi is cosine of 360 is 1. J of 2 pi is 0. Sine of 2 pi is 0. Do you all follow me, class? Or 360 degrees. So that means that's 1 and that's 1. So that means V0 plus is equal to 8/3 divided by, and here it's going to be 1 plus the reflection coefficient times 1. These are both 1, and that's 8/3 over, and 1 plus reflection coefficient was 2/3, right? Class? Was it?
Reflection coefficient was 1/3.
1/3, I mean, 1/3,
1/3.
sorry. 1/3, so what's that? That's 8/3 divided by 4/3, right? Or we get 2. V naught plus is 2, correct? Now I'm answering your question now. I needed that to answer your question. So the next question is, what is the voltage at the load, right? I think? Or voltage at the input we got already.
Yeah, the input into the line, the load into the line.
The input was just what?
It was it 8/3?
8/3 volts, right?
Yeah.
All right, I hope that's right.
Yeah, that's right.
All right, so how do you get it at the load? Well, go back to this equation right here. Right. At the load, Z is 0, right? So it's going to be what? V0 plus 1 plus reflection coefficient times 1. Exact. You follow me on that, class? So at the load, yeah, V of Z, for Z equals 0, is going to be equal to V0 plus, which is 2, and it's going to be times 1 plus the reflection coefficient, which is 1/3, right? So that's 2, right? 2, and then it's going to be times 4/3, so it's 8/3. So it's exactly what it is at the beginning. Is that the right answer?
I think so, yeah. I gotta make sure I have
Take
it.
a look. It has to be, by the way.
Can you explain that one more time, if you don't mind?
Do you follow me on this formula, right?
Mm-hmm. Yeah.
How we got V0 plus?
Mm-hmm.
So put in V0 plus, so that's going to be what? That's right here, 2, right?
Mm-hmm.
So I got 2 in here, right?
Mm-hmm.
Now, at the load, Z is 0.
Oh, yes, so that
E to
goes
the
away,
0
so
is
it's
1, so 1 plus reflection coefficient, right? Times 1 is 4/3, times 2 is
Okay.
8/3.
Okay, so it's just B0 plus times 1 plus the reflection coefficient, right?
Yeah, at the load. Now, he asks at the middle of the line, right?
Yeah, yes, middle of the line too.
This is an interesting one. Let me do it over here. You can get it anywhere, but this is interesting. So, halfway between the load and that, when we look at this, we have V of Z is equal to V0 plus, which is 2, right? So it's 2 times E to the, now I'm going to put it down right, minus J beta Z plus reflection coefficient times E to the plus J beta Z, right? But when you're at the middle of the line, if that is 0, where the load is, the middle of the line would be L over 2, but it would be negative. Z would be minus L over 2. You all follow me on that? Huh?
Why is it minus?
Remember, this load is at 0, right? This value here would be negative. Z would be negative. The line's total length is just lambda, but when I have to account for the position Z, because we locate that at 0, but that's positive Z, that's negative Z. Just by, we're doing this only for convenience. The middle line is L over 2 in length away from the load, but it's actually minus L over 2 Z-wise. So we go up here, and now we say the voltage at the middle line at Z equals minus L over 2 is 2. Now take a look at this. I have E to the 1. Beta Z would be what? Beta is 2 pi over lambda times minus lambda over 2, right? That would be the value of Z, lambda over 2, total length is lambda. What's that going to be? That's minus pi, correct? You all agree with that? What's minus pi? What is E to the minus pi? Think about E. Remember that? You could take cosine of minus pi plus J sine of minus pi. It's what?
It's just a 1.
Y'all follow me?
Yep.
Isn't that right? Actually, I'm going to put it this way. Hold it. Sorry. If I have this, I have, I think I made a mistake here. If this is E to the minus J theta, if this is pi, it's right here, so it's actually minus 1. I'm so sorry about that. You agree with that, class? And so here, then you can get it by just taking e to the j, let me try that again. E to the j theta is cosine theta plus j sine of theta, right? So if I have e to the minus j, I'm sorry about that, j I give me 1 second here. Sorry. Something's making sense when I take that. So, if that's cosine minus pi,
That's 0.
that's positive 1. Cosine's an even function, right? Wait. I'm thinking about this. Yeah, it is minus 1. My bad. I'm convinced. All right, so this is -1 and this is -1, so it's going to be 2 times -1 plus 1/3 times -1. That's going to be minus 8/3. Isn't that right, class? Is that the answer he has? Or he'll have 8/3 at 180 degrees, something like that? What does he have for that?
It's just inverted. Oh, I'm not sure. Need to check. The answers are on here.
You all follow me now? Sorry, I'm a little tired. It's the cosine of pi, and it would be -1. I'm sorry, my bad. Do you agree with this, class? Is that the answer, by the way? Or no? Bill, do that one.
I don't have the figure, I don't have a textbook yet. It arrived today.
I put up the answers, didn't I?
It didn't have the
Yeah,
figure though.
you
It
did.
didn't have the picture.
Yeah, but I mean, I'm looking to see if that answers. It's gotta be minus 8/3, or 8/3 at an angle of 180 degrees, or
I think
-5.
so. It just says 8/3.
What does he want, the magnitude, or what?
It's just in the book. It says it just wants the phasor voltage at the middle of the line.
Yeah, but it has a minus sign associated with it. It'll have a magnitude of 8/3 for the phase. It's gotta have a negative sense to it.
There's lessons. It's 1, 1 is 1. He just,
Wait. I put. No, that's right. That is right. You can check me on that, but that's how you get it. So what's the, any other problem? You can check that, but that's how you get it.
No, that's it. That's all I got.
Anything, any other questions? By the way, remember, this kind of problem, this is usually one of the problems that people stumble on. It's called a complete circuit, and if you want the voltage at the load or the source or anything, you have to get the input impedance using the equation I erased here with Zn equals that complicated thing. And then you have to find V prime and set it equal to the total voltage at that point. Remember that, because people mess that up. Let's see. I don't know if I gave you terminated lines and complete circuit. Did I give you problem 22? 2.22, we did, right?
Yeah, we just did
That
one.
was that.
Yeah.
That was a complete circuit one.
Okay. All right. So, give me 1 second. We did input impedance, standing wave ratio, complex loads are trivial things. The complete circuit we did, talked about Viswire. Okay. Now we're going to do something. I should have probably sent you a Smith chart, and I will, but if you look in your books on page 63, there's something called a Smith chart. Now, I can go through how they actually develop it. He does it in his book, but I want to show you how to use it. Because the development isn't as nearly as important as understanding how to use this thing. This is a graphical method for calculating all sorts of things, and it does it very quickly, faster than probably you can with your calculator or anything like that, unless you're writing a program for this. So I want to show you this and how you use the Smith chart. And I'll send you some videos, I'll post them, but this is really good stuff. And I always give a couple of Smith chart problems. I'm going to send you this so you can print them off and bring your own. Got one other thing to tell you about Smith charts. You need a sharp pencil and a compass and a straight edge. So you can get a good compass, not one of those cheap ones. Go get a good compass over at the bookstore. You'll need that with a sharp point. And then you need a straight edge, a ruler with a good edge on it. And after that, that's it. So let me go through this. And you can look in the book if you've got a book. But I'll show you how to use this thing. really you want to know how to use it. So, this is a smooth. Oddly enough, name for Mr. Smith. Who would have thought? So here's what the Smith chart is. It's a big old circle like this, and it's going to have a center point. Now, what's actually shown here are trajectories of the normalized impedance, for starters. So if we have a circuit, and we have a characteristic impedance Z0, and we have a load ZL, what we do first when we use a Smith chart is we find something called the normalized input impedance, which is ZL over Z0. A few other things, I'm going to have to just push this out, and it all makes sense in a bit, but I'm going to tell you everything. So what this is really plotting are trajectories of the reflection coefficient. Now, you don't have to write this down, but the reflection coefficient, it's actually reflection coefficient at any point. Reflection coefficient is ZL minus Z0 over ZL plus Z0. Just watch this. You don't have to write this down, just listen. So if I divide top and bottom by Z0, I get normalized ZL minus 1 over ZL plus 1. Do you all follow me on that? Now, ZL itself will have a real and imaginary part. Just try to appreciate this. That means the reflection coefficient here can be rendered as some, I'll call it RL plus JXL, normalized value of the input impedance minus Z0 over RL plus X plus JXL plus Z, or plus 1, pardon me, plus 1, my bad. The only thing I'm doing is breaking ZL up into a real and imaginary part. Follow me? Now, we can go ahead and remember, if I go ahead and I'm going to just show you how they mess with it, I'm going to get the real parts and the imaginary parts. So if I went down here, I would have 1 plus RL normalized plus JXL, and upstairs I'd have have RL minus 1 plus JXL. Can everybody follow me on that? Now, if I want to get something that just has complex values up here and real values here, in other words, I would multiply it by the complex conjugate. I'm trying to do this. You don't have to do this, but I want you to appreciate why. So if I multiply top and bottom by the conjugate of this, or 1 plus RL minus JXL over 1 plus RL, it's always small r in the book, but it looks like a V if I write it here, minus JXL. Probably remember this. What you actually see is downstairs, I'm going to get rid of these J terms. This will be times this times this, and this times this will cancel. Then I'll have this times this. I'll have J times minus J, which is going to be 1, so it'll be plus XL. I get everything positive downstairs. You with me, class? Then upstairs, I have something where I have a real part and an imaginary part. Can you all follow me? You can look at the proof in a minute. So what happens here is they plot where trajectories, without getting into too much of this, just try to appreciate. I just showed you this at the load, but if we allowed this to be anywhere, not just at the load, this would be multiplied by an e to the j, and it's 2 beta times the length. And I don't want to go there right now because it'll get too confusing, but there's a way. And what happens is you plot trajectories of the real and imaginary part. So here, you're going to see a trajectory, and this will be right when it goes through the center of r equal 1. Now, by the same, it's just the real part is 1, and it's anywhere on this circle. Try to appreciate this. You might as well draw a horizon. I call this the equator. Then, by the same token, there will be complex trajectories that will look like this. And this will be plus J1, and coming down here at the south pole, minus J1. Can everybody follow me? Just appreciate this. There will be bigger circles. The bigger the circle, this will be R like 1/2. Keep going. R maybe 1/4. And if you look in the book, you'll see something like this. Then you'll say larger values here, this would be like minus J2, minus J3. All the minus J's are south of the equator is the way I say. All the plus J's are north of the equator. You'll see something where this is going to be plus J2, plus J4. And then you'll see them come out here. This would be like plus J3/4, and this would be minus J3/4. Take a look for a second and see if you can see that in your book on that. Can you all see that? You don't have a book. You have your book here? Or?
It's coming tomorrow.
All right, well, let me just show you this so you know what I'm talking about. Here's the Smith chart. Share it among yourself. Take a good look. Make sure you see what I'm talking about. Do you have a book back there or no?
Yes, sir.
Okay. And you got one or no?
I don't know.
Well, I want to make sure he sees that. Take a good look.
I have a Smith chart if you just want.
You got a Smith chart?
Yes, sir.
A real one?
Yeah.
Hand it to me. I'll give it to you. Thank you. Have I taught you before?
Yes, sir.
I thought I did. You look very familiar, but what did I teach you?
It was last semester. I got a concussion. And had a,
Oh, yeah, I remember. Oh, I'm very sorry. All right, can you just recognize all these things, these trajectories, this is plus J up here. All right, all these are strict real values. Okay. They're hard to look at. I appreciate it. All right, now when you look at this right here, the Smith chart, here's what happens. See this value here? It's going to have a real and imaginary part. You all with me? We're going to do something. So what you have to do is plot that point. Let's just assume this normalized value for sake of argument. Let's assume ZL normalized is, say it's 2 plus J1. Right? Where would that be? Well, first I locate the real circle 2. If this is 1, the real of 2 will be inside this. This will be R equal 2. If you got a Smith chart, take a look at that. Can you see that? It'll be R equal 2. It's inside the 1, so it's a smaller circle. It's closer to this point here. You all see it? Now, next I find J equals 1. Well, here's the J equal 1 trajectory. So this would be my first point in the Smith chart. And I always call that, just label it ZL. Can you all follow me? Just take a look. You're going to get acquainted with the Smith chart in a hurry in my class. With me? Can you see it?
Yeah, I got you.
All right, see where the intersection is. This is an approximation. So now what happens is, if you draw a line from the center of the circle to this point right here, that will give you is information about a length here, and I'm going to call that would be proportional to the magnitude of the reflection coefficient. And if you come out here, you're going to see an angular measure, theta, and this is going to be positive this way, and you'll see you'll actually have the reflection coefficient, magnitude, and angle. Now it's not quite that easy. See how I have this length here? If you had your compass, you measured this at the bottom of the page, there's going to be something called reflection coefficient or voltage reflection coefficient, like you have CERF or something like this at the bottom. Let me show you what I'm talking about. You look down here, you're going to see that reflection coefficient E or I at the bottom of yours? And I think reflection coefficient E or I, here's why it says E. In Britain, E is a symbol for voltage. I is still current, all right? Now the reflection coefficient for current or voltage will be the same. Can you see it in there at the bottom, right down here? See it? All right. Now if you take this length here, you go down there and you put it here, you'll see the actual value. Can you see that? That will give you the value and magnitude of the reflection coefficient. Now if you come up here, I'll show you. You see these angular, you're going to see angular measures there. You see how this is 0 right there? And it goes, that's 15 degrees, 10 degrees, 20 degrees. You can see if you draw a line straight through there, you can estimate what the angle is. Do y'all follow? Now remember, reflection coefficient in general, you don't need that to do this. You can get it this way. You can just say reflection coefficient is really just ZL normalized minus 1 over ZL normalized plus 1. And your calculators will do that, won't they? I mean, that's, your calculator will do that. ZL will have a real and imaginary part where it's normalized, but you can get that. But this is where the Smith chart gives it to you, right in the bottom there. Now, that doesn't do a whole lot for you yet, but you're about to see why Smith chart is so important. So next, I don't even go through this anymore. You can go through it. It's just trajectories. Remember how circles, and I'll just say this. So, y'all follow me? I could get a real and imaginary part that would have, basically it would have values of XL and RL, right? Well, in a circle in general, that's x squared plus y squared equals c squared, a constant, right? For r's, we have real and imaginary parts. So RL, but now it's going to be RL minus 1 squared plus, and here it's going to be XL squared equal a constant. What happens is these trajectories I'm talking about are really plotting the real and imaginary components at a constant reflection coefficient. I'm not going to spend much time on there. You can read this for your own. But that's where this stuff comes from. So next, here's what happens with Smith charts. I don't want to spend too much time on this because I don't need you to focus on that. I have to show you how to focus on how to use these things. So remember, this is my first point right here, right? Where I come in. Next, if you take and extend this right through here, you're going to see something on the outer rim that's going to be WPG. That's wavelengths towards generator. Please take a look. I should have brought you, I got you Smith charts ahead. Do y'all see that? So if you have wavelengths towards generator, if you're at the load, the generator's down here somewhere, right? Plus or minus, this is going to be V of the generator right there. So when you plot this point, you take a line out here, and wavelengths towards generator, you're going to get something that's going to, I call mile markers. But if you look at the outer rim, I'll show you what I'm talking about. I'll show you first. First you got to see this wavelengths towards generator. Now if you look, if you drew this, just that's the case, so that's going to come out about here, right? You can see I'm about at 0.218, something like that. If you look on yours, you're going to get a value on here that's about 0.218. It's in lambda. It doesn't have lambda there. You all see this? Take a good look on the outer rim. Can you see that on yours? Yours is kind of, can you see it?
Yeah, I got, I'm looking at 0.212, but
212? Maybe yours, you're probably right. Do you have the ability to draw a straight line on that thing?
yes, sir.
So it's 212? 212?
Yes, sir.
Okay, I'll trust you. All right, now that is your starting point. So that 212 is like a mile marker on a highway. Right here, the mile marker where this load is 0.212 lambda. Now, if we move away from the load, and I'm going to show you what I mean. Here I am. I'm moving this way. I'm going wavelengths towards generator, right? So, in yours, I'll show you on yours. If you look at that, you got wavelengths towards generator on here. That means I'm going to start there. I'm going to move this way. Can you see the arrow there?
Yes.
All right, so we're moving clockwise. Here's my first point right here. And now I'm going to just make up something. Suppose I wanted to move a quarter wave, lambda over 4 way, and I wanted to know what the input impedance is right here. So I want to know Z in here. There's a lot more to this. Do you all follow me in that? All right, so now I take a quarter wavelength is 0.25 lambda, and I add it to that mile marker. Do you all follow me? So what do you get? I don't know. So you get 0.25 plus 0.212, and what's that gonna be? So it's 0.462 lambda. Do you agree with that, class? I know you don't have your compass, I should have mailed this to you, but work with me on this one. You all good with that? Now, if you look, that's 212, keep going down here. This is 0.25 lambda. Y'all see that? That's a mile marker. Keep going around, and right about here somewhere, you're gonna get 0.462. Can you all see that lambda? Take a good look, roughly. You with me? Now, here's how you figure out the input impedance from this. There's so much more to this. This is the beginning stuff. You take your compass, put it here, and you make a circle of that radius, of constant radius gamma, or of the point between the center point and this point. Just zip it around. You all follow me? All right, now, next thing you do is you take your straight edge and you move it through here, and this intersection point would be 0.2. And that would be the normalized input impedance right there. Take a moment and just appreciate what I'm saying. All right, now, your calculators would do this. Some of the stuff I'm going to show you, they don't do so easy. But for that, your calculators would do this, won't they? So now you have the input impedance, normalized input impedance right here, whatever that is. Can you read that, by the way? You were in my class last time. What's your name again?
Chase
Chase
Simpson.
Simpson.
Yes,
All right, can you read that on yours if you ever have the ability?
Which one?
Yeah, when I go to 0.462, and you take a straight, do you have the ability to draw a circle or not?
Isn't that just Z all over? No.
Now, we move from here to here, right?
Yes, sir.
So it's around the trajectory. You're moving this way, literally on that circle, on this circle, and you're moving right to that.
Yes, sir.
I know some students have a Smith chart thing on the, where they have the Smith chart, they can put a circle, straight lines, everything, and they get exactly the value. It's kind of nice. I wish I had it. Everybody with me on this? What do you get, Chase? Any estimate? We could actually calculate using Z naught times ZL plus J Z naught tangent of beta L over those things and then normalize it. But I just want to get the value. Can you get it?
0.4 minus.
All right, hold on. This is 0.4 minus J1. Small.
0.3236.
0.36? Wow, okay. Now, that value is...
I'm sorry. 0.24.
Okay. Let's assume that's my normalized Zn, all right? To get the value of Zn, I want you to pay attention to this. To get the actual value of Zn, what do? I take that and multiply it by Z naught. See how I normalized in the beginning? Now I multiply it by Z naught. So the actual value of Zn there would be Z naught, whatever it is. Say Z naught's 50. So if it's 50, it would be 50 times that, which is 0.4 plus, or minus, pardon me, minus J 0.24, right? So what is that? That's 20, right? 20 minus J, oh boy. 25, 12.5, about 12.46, something like that, minus 12.46 ohms. Is that about right?
50 times 0.24?
50 times 0.24.
It's just 12.
Is it really?
I got 12.
Okay, good. I'm glad. All right, 12. Now, how accurate is that? Well, we actually know that Zn for that line, if it is 50 ohms, right? And I made up, I said the normalized was 2 plus J1. Yeah. Oh yeah, go ahead. Come on. It will not, or it didn't for my 9:45 class.
So you're
Sorry,
trying
guys.
to use personal laptop or the document camera?
I had, none of them would work. We tried it. You can try the document camera, do anything you want. Anyway, let's continue on here while these guys try to fix that. Good luck. And you can turn it on, don't worry, it ain't gonna bug me too much. Anyway, if you actually calculate it, now this is what we got so far. And I'm kind of trusting your ability. If we looked at the actual value, remember I had this normalized at 2 plus J1 to 50 ohms, right? So that means the actual load impedance was what? Well, it would be 100, right? And it was plus J1 or plus J50. Y'all follow me on that? Get your calculator. If you have a calculator, try to do this with it. Because this is where people mess up on their calculators, left and right. All right. Now remember, this is what we got using the Smith chart. So if we use our calculators, and just watch me do this, then I'm going to get what? Zn, this is going to be normal, or this is not normalized. It's going to be Z naught, which is 50, right? And it's going to be times ZL, or 100 plus J50 plus J Z naught, right? I'm going to leave it as Z naught, over, and this is going to be Z naught plus J, and this is going to be 100 plus J50 times, and this is tangent of beta L, tangent of beta L. Now, what is beta L for this one? Well, beta L, remember the length of line I put here was 0.25. Y'all remember? So that's what goes in here. So if I have beta L, I have 2 pi over lambda times L, which is lambda over 4. You can see that this is going to be what? Pi over 2. Agreed? Please just watch this. You'll get it in a second. Everybody with me? Take a moment. What is the tangent of 90 degrees? Infinite, isn't it? Going to infinity. It means these two values are going to asymptotically become enormous. Y'all follow me on that? It means these two are negligible. Y'all with me? The tangent are going to blow up to infinity. So what am I left with? Just watch this. Now I'm left with Z naught times Z naught, or Z naught squared over this, right? The tangents will cancel. So I get my input impedance, just watch me on this. Zn itself is going to be Z naught squared, the J's will cancel, so that's going to be 50 squared over this, which is 100 plus J50. Can you tell me what that is? So it's 2,500 over 100 plus J50, what do you get? Anybody?
I got 20 minus J10.
All right. We calculated 20 minus J12 with a lot of eyeballing, right? 20 minus J10 is the actual. You see how close it is? And if you use a good Smith chart, you won't be able to tell the difference. But this is how a Smith chart works to give you the input impedance anywhere. Y'all with me? I got something. They're going to go nuts trying to do this. I spent the morning, about 10 minutes in the morning, trying to figure that thing out. He was in the class, too. It was like, this is a disaster. Y'all follow me how crazy it is?
Yeah.
Nothing works. It's like, what? And go to that thing here. Let me just show you. I got to help you. Just show them what I've gone through. See this right here?
Yeah.
Watch this menu. See that menu right there? All right, you can, well, see, you see how you can, try to get this thing. All right, now I would think one of these would work, but it doesn't.
Yeah, not one of them.
You try that?
I think it's the
Yeah.
main
Our
like, shot.
The what?
The input switcher.
Input
The thing that actually powers this seems to be dead.
Okay, can you guys fix it?
Probably not immediately, but we're
That should-
By next class, by Wednesday, or what is
probably
it?
by Wednesday.
Wednesday. All right.
Yeah, but
By Wednesday, huh?
We should be able to.
All right, can you shut it down?
Yeah.
Yeah.
Thank you. I appreciate it. I'm glad it wasn't just me going nuts. That was a frustrating thing this morning. I had a PowerPoint, I got everybody ready.
We'll stay here because I think we might need some more info from them, but we'll just address it.
Yes, you can hang out. You learned something too. All right. Now, I'm going to tell you some things about the Smith chart, and I want you to be attentive. And I know these classes get a little long. Y'all follow me at least up to this point. The first thing you do is get normalized impedance. After that, plot it. Then you might as well just draw a circle around that point from the origin to that point, your trajectory. Then you shoot a line out there, find wavelengths towards generator. Then if you're moving along this arc. Now, some things I got to tell you. I want you to listen real carefully here. As you're moving along this arc, when you hit this point in the equator between the center and this edge, that, if you look at this right here, you'll get, now I want you to do it with me, estimate it. And by the way, Chase, can you just give me this value? Take a look at this. Take a look at where it crosses here. Tell me that value.
3.
Huh?
3.
You know what that is? That is the standing wave ratio. That's so important. That will give you the standing wave ratio. One other thing is when you move a distance from here to here, in terms of wavelengths, from here, which is 0.212, to here, which is 0.25, that's 0.25.
Do you mind if I ask when this class ends? Just in case we got to come back and replace
In about, let's see, is it about 2:16?
It's 2:30 is what it is.
It ends at 2:30,
Okay.
but you got about 10 minutes or so.
it?
Good luck. I feel for you. Because that thing's a mess. So, just one last thing about this. So, I was building up to this presentation this morning with PowerPoint, and then right when I'm ready to do the ta-da, nothing. I had a PowerPoint and everything was a disaster. Anyway, it happens. But you all follow me so far? So this is the point where the standing wave ratio is maximum. Not only that, I mean, this will give you a standing wave ratio. When you move from here to here, the voltage is a maximum on the line. You got that? You can get the standing wave ratio, and you got, well, that's how far you got to go to move to get the maximum voltage. So you get, from here to here, I'll tell you where the maximum is. Now, listen up. This is real important. Every time you go around this circle, from this point and all the way around back to it, it's exactly half wavelength. What this circle is here is the plot of exactly, remember I said every half wavelength, everything repeats? So if you move along this trajectory all the way back to where you came from, you'll move exactly half wavelength. And when you move from here to this point, what is that? 0.25 minus 0.212 is what? 50 minus 12. So it's going to be 0.36 lambda. Do you all follow me on that? From here to here is 0.036 lambda. Just add it to 0.202 plus 0.036. Do you all agree with that? All right, that's where the maximum occurs. The minimum will occur exactly a quarter wave length away. So when I'm right here, that's the minimum voltage on the line. It's real important to appreciate this. We can get the input impedance anywhere on the line. That's sort of a Smith chart in a nutshell for you in the simple way that you can do business with. Y'all with me on this class? I'm going to send you a very good Smith chart. You can look them up online, but I've got a really good one Whitworth got for me, and I'm going to send them out. You can print them and bring them in yourself and use them. And, you know, you've got, what, are you using a special app for that, or how are you doing it?
It's an app called Good Notes, but it doesn't, like, the center of the circle, I had to estimate that.
Can you send that to me, and I'll send it to everybody?
It costs $5.
Oh, never mind.
Yeah.
I mean, there's stuff out there. I got to level with you. You know, we're just touching what this thing will do so much more. I mean, you can do impedance matching, all sorts of stuff. You can learn more about a transmission line when you're doing matching with stubs. You'll find out how we get rid of reflections and stuff like that in a heartbeat with it. Even the best equipment, if you get Agilent equipment or anything like that, when it's doing any kind of high-frequency network analysis, it'll have a Smith chart come up where you can, you'll literally look at stuff using a Smith chart. It's ubiquitous, it's everywhere. Everybody uses these, and you have to know. So, next, all right, more with Smith charts. Whitworth's going to have some problems in his book, but he's going to ask things like, and here's where it gets good. So, you know, if I have an impedance here of, say, 100, say this is ZL, 100 plus J50, right? That's if this is 50 ohms here as the line, then if I normalize this, this would be what? This would be 2 plus J1, right? ZL. Agree, class? Let me erase this. I'm going to show you how these impedance match this. Just bear with me. Try not to cover too much in one swath, especially when you don't have Smith charts to ask questions and you haven't done any problems. So here's what my game is. So I want to find out what I need to do, what I need to add to this line here. I'll call it Z, maybe I better call it JX. And this JX is going to be something I'm going to add. So the input impedance here is 50 ohms. So I want Z in to be 50 after that side. In other words, now if it's 50 ohms, think, if it's 50 ohm line over here, then the reflection coefficient is 0. Do y'all follow me? If you could get 50 ohms here, coming from a 50 ohm line, the reflection coefficient would be 0. Do y'all follow me? Real important you see this. Okay, so how do you do it? Here's how. We're going to add it in series. So here's my Smith chart that you were just introduced to. And here, I'm going to show you. Try to. And here's my J1 circle. Here's my minus J1 circle. Here's R equal 1, not drawn to scale. And now I'm going to start talking about it. Remember, the first thing is find ZL, which is going to be 2 plus J1. Everybody with me? So 2 plus J1 is, here's 2 roughly. J1 is here, so this is 0.1, that's ZL. That's where I enter. Now I drew a circle, something like this, didn't I? And I said this is going to be my constant reflection coefficient circle. Y'all with me? Mm-hmm. Now, hear me on this one. If I go, and I'm moving this way, I'm moving wavelengths towards generator. If I hit this point, now realize that's the one circle. Y'all see that? Please be attentive here. This would be the one circle I hit. I move from here, this is 0.1. Here's my second point. I intercept the one circle. This is going to have a value of 1 minus J something. You can see because it's going to have a minus J. I'm in the southern hemisphere. And the way you do it, you chart where this trajectory intersects this trajectory. And remember, this is constant reflection coefficient, right? Y'all with me? This is a circle, really. I'm trying to show you. So now I have 1 minus J something, right? Hear me. Well, what if I added a plus J something? Let's call it 1 plus JX. Hear me? Now, in series, if that's impedance, if I add here, if that's 1 minus JX, if I just add JX, then I get a normalized impedance of 1. You all with me? So what impedance element has a plus J?
Inductor.
An inductor, right? An inductor L has an impedance of J omega L. A capacitor C has an impedance, and this is a Z. This has an impedance of minus J over omega C, right? Now, this value here, whatever it is, and I don't know what it is, but I'm just trying to get through this before these guys come in. That's normalized. With me? So this minus JX is actually the actual impedance, whatever it is, call it capital X, over Z naught. You with me? So one thing I can do is to calculate this value of impedance. Remember, that's minus JX here. I'm going to add a plus JX. And I know mine is normalized. So what I do is take the inductor's impedance right here. I have it. The inductor's impedance is J omega L, right? And I normalize it, because my impedance over there was normalized, divided by Z naught, and I set it equal to Jx, the x value that would be here if you looked at this trajectory. You all follow me? And then we calculate the value. The j's are going to cancel. We can calculate the value of L would be x, the value where this intercepts down here, and it would be times Z naught over omega, which is 2 pi f. So they have to give you a frequency. And then it would impedance match it, but it would impedance match it if I put that inductor in there only at that frequency. Y'all hear me? It would, because as frequency changes, the impedance would change of that inductor, and therefore it would not be impedance matched for all frequencies. I'm getting short on time, but you all with me on this class? Now, in my book, I'm trying to show you guys. Everybody have access to this kind of stuff? You do. All right. Now, if you look, and he goes through what I was talking about, the trajectories and stuff like this in the early part, page 65, 66 and stuff. Then he shows using the Smith chart. Now, that's what I'm trying to get through right now, and I'm trying to do it in a way where it's most meaningful to you. And so what I'm going to do now is, I think we can break off, because I'll probably hold you a little late. I'm notorious for that on days. I'm going to give you some problems on this one. I'll send you the Smith chart and ask you to do them for next class. On Friday, the quiz will be on transmission lines and Smith charts, okay? So I want you to make sure you keep in touch or stay up and current with this. If you know where the other guys are in the class, there was one guy back here who was Asian. There was somebody else was here. I can't think of him. What's his name? But just, you know, give him a hint. Stay in tune, stay updated, because this stuff can tell you if you don't stay on top of this, you can really get yourself in a hurt, because in the summer it goes by quicker. We only have 10 weeks to cover 15 weeks of material, and you can try, but you can't really cram effectively. Most people who try cramming really get messed up, especially with some of the stuff that's coming out. Okay. Did y'all get something out of this? Any questions before I break it out? I could keep going, but honestly, until you work some problems, I can't really address this. I wanted to just show you at least the thought process with this. Has anybody had Smith charts before for any reason in your lab work? You have? Then what?
At my co-op.
Where was it?
Neptune Technology Group.
Oh yeah, I know Neptune real well. Water meters.
Yep.
I know them real well. Wireless water meters. Good. If you've had them, that's great. That make sense to you today?